This example gives us a function already in the Laplace frequency domain, and again we want to solve it for f of t. We want to take it back into the time domain to get our complete solution. If we're at the right hand side, we don't want to right away just try to take the inverse Laplace transform though, because looking at the format of the right hand side, we have an s in the numerator and s in the denominator, and we don't see anything like this directly on the Laplace transform table. So we're going to have to do some algebraic manipulation to make it look like a term or terms that do appear on the Laplace transform table. In this case though, the degree of the numerator is 1 and the degree of the denominator is 1, and we only have one term in the denominator, so we can't use a partial fraction expansion for this. We're going to want to do something different here. But in this case, when the degree of the numerator and the denominator are equal, and in this case they're both 1, one thing we can try to do is simply doing polynomial division to separate this into two terms. So I'm dividing the 3s by the s plus 5. So 3s, and I'm doing division here, and divide by s plus 5. Now what I want to do first is the 3s, I do want to again explicitly put in the constant term, which will be 0, but this will make it easier when I do the actual division. Now this polynomial division is pretty straightforward because I only have this first order s, but the concept of it would carry over if we have higher order s terms in the numerator or in the denominator if we wanted to have something higher order. Now what we do for the polynomial division is we really only care about the leading terms. We have this s on the outside, or 1s on the outside, and this 3s on the inside. So what I want to look at is, again, just these first terms. I'll mark those. I want to see how many times does the outside go into the inside. So how many times does s go into 3s? Well, that's going to go in 3 times. Right, so what I'm going to do then is subtract 3 times the s plus 5. So 3 times s is 3s, and by design this will go to 0. But then I'll have a 3 and a 5, that will be 15. So 3s plus 15. Right, now if I carry through this subtraction, I have 3s plus 0 minus 3s plus 15. 3s minus 3s is going to be 0s, and again we did that, we want that to happen. So 0s, but then we have a 0 minus a 15 is minus 15. Right, so now normally we would continue this, and that's going to happen when the numerator is of a higher degree than the denominator. We're going to be able to do another division. But here we have to be done, because what do we have left? We have this negative 15 left, but on the outside our leading term has an s in it. So we have to stop once the stuff under the division is now of a lower order than what we are dividing by. So we have a negative 15, we have to stop. But this tells us we can now rewrite our f of s and split it into 2 terms, kind of the whole part and the fractional part. So this is going to equal the 3, and then what we have left over, we have a minus 15 over s plus 5. So kind of that's just the remainder is going to go over the divisor, the s plus 5. S plus 5, and add those together. Okay, so we were able to do the polynomial division, so I have a whole number, 3, plus a negative 15 over an s plus 5. Now I have terms that do appear on the inverse Laplace transform table. So I will be able to do the inverse Laplace of both sides. So taking inverse Laplace transform of the left-hand side, this f of s, and the inverse Laplace of the right-hand side. So I will skip some of the steps here. So right away, the first term, I can pull the 3 out. So I'll have the inverse Laplace transform of 1. And then I'll have a minus 15, which I'll pull out, times the inverse Laplace transform of 1 over s plus 5. All right, so the negative 15 I pulled out, and the 3 I pulled out. On the left-hand side, that will just be f of t when I do my inverse Laplace transform. Big F of s goes to f of t when I do the inverse Laplace transform. Now I have 3 times the inverse Laplace transform of 1. So remember, I'm going from the right-hand side to the left-hand side. This is s and this is t, or time. So this will be 3 times delta of t. That's the Dirac delta, or the impulse function. So 3 times Dirac delta minus 15 will come along, and now I need the inverse Laplace transform of 1 over s plus 5. Well, that's going to be 2 on the Laplace transform, on this Laplace transform table. So I will be left with an e negative to the negative 5t power. And that is our complete closed form solution for our f of t. We have a Dirac delta part, and we have this decaying exponential part to it. And we're going to see functions like this when we get into Unit 2, and we look at first order systems. We're going to look at fractions that look just like this, and we're going to be looking at their solutions. But using Laplace transform, this is how we can go from what was given to us, this first degree on top, first degree on the bottom, which doesn't appear on the Laplace transform table, and using an algebraic technique, in this case just polynomial division, able to rearrange it into 2 terms, each of which does appear on the Laplace transform table, so that we can get our closed form solution in the time domain.